Sure, I don't know which one. But we'll be talking about first and second derivative tests. We are learning how to apply derivatives so that we can do cool things with them. And last time in 4.1 we talked about minima and maxima, which is minimum and maximum in a function. We can have local, we can have the global or absolute. And we found a method which these min and max occur. So what we said earlier is that if you set the first derivative equal to 0, which means that you are forcing the slope of the tangent line to be horizontal, right? Horizontal lines have the slope of 0. In that case, you are detecting either a minimum or a maximum. So both slopes in this case are 0. So the tangent line slope is 0. And we went through the procedure. We set the first derivative equal to 0. We find x's, which were critical numbers. Then we find their y values, which were critical points then. And then those critical points are either min, max, and I was also hinting on something called inflection point. So once we have those points, we need to be able to say without too much trouble whether they are min or a max or neither. And that is done through the first and could be done with the second derivative test. So that is what we are learning today. So the first derivative test states, so let a, I have to call x equals a, be a critical number nope. Well, okay. And x equals b, a test point away from a. Here is the graphic representation of that. So if a is here, b can be anywhere. Before or after a, that doesn't matter. Should be everywhere. Well, we'll see. So now, if f prime of b is larger than 0, f of x is increasing. If f prime of b is less than 0, f of x is decreasing. And obviously, if f of b is equal to 0, then you have a critical point, which is f of a. This is much shorter and more condensed than what your textbook is offering. This is all you need to compute. And once you know when the function is increasing and decreasing, you can quickly come up with the idea what is the minimum or a maximum. So let's just test this on the easiest function that we know, x squared. So let's say f of x is equal to x squared. Its derivative is 2x. We set that equal to 0 to find critical numbers. So x is equal to 0, which is the critical number. And then when we find f of 0 is equal to 0 squared, which is 0, we have 0, 0, which is critical point. Now this critical point gets to be min or max or that inflection later on. So how do we know which one it is? Well, we draw we put the number line down, x, and we put the critical number down, and we make a little box above it, let's say. So you have two boxes now. The line above 0 is not y-axis. It is just separation between two worlds before and after 0. That's all it is. So now we are going to pick those b's that will be used in a test. Pick any value before 0, -1. Let me put it red. -1. And then over here, +1. So we pick values before and after 0, and those are the test points or test values. They're not points because no y-axis coordinates there. So test values. So what do we have? We are going to test f prime computed at -1. Well, f prime is 2x. Computed at -1 is just -1 for x. Becomes -2 less than 0. So function is decreasing. You draw decreasing arrow. F prime at 1 is 2 times 1, which is 2, which is larger than 0, which by our theorem that we have up there, procedure says that f of x is increasing, so we draw the increasing piece. And it should be common sense now that at 0, 0 you have a minimum. We don't even look at the function at all. We just looked at this calculation. We looked at what the derivative does, and then we computed the test values in the derivative, and we found that the function is decreasing, the function is increasing, and then the function is falling down and then rises. You had to hit the minimum and bounce up. So this implies minimum. Now, we're lucky that x squared is easy function, so we can graph it and confirm. But as I said, this is one of those problems, procedures that you would use for something that you don't get to graph. Now, we get to graph everything today, right? Except when we have our little scenario of a desert island and so on. So that was that one. You will quickly see that this procedure doesn't work on something that does not have min and max, like let's say e to the 3x. We can do that. So f of x equals e to the 3x. It's exponential function, does not have min or a max. And we immediately find the derivative. So let's just write over here min, max, right? So that's what we're looking for. So we find the derivative, 3e to the 3x, and we set that equal to 0, which gives no solution. So no solution implies no critical points, which implies no min max. But we can still check whether the function is increasing or decreasing by running the first derivative test. See, first derivative test is not a test for you to find min and max. The first derivative test detects where the function is decreasing, where is the function increasing, and so on. That's what it detects. But we get to use it to figure out min and max. So this function here has no min and max, but I can still go and pick any value for a test point on the entire domain, because entire domain is the single function. Otherwise, if it had min and max, derivative would find it. So we have pick a value, whatever, x equals what? Value. Come on, give me a number. 4. 4. So pick a value, x equals 4. So we do f prime at 4, which is 3e to the 3 times 4, which is 3e to the 12. That's larger than 0. I don't care how much this is. I know it's larger than 0. E to the 12 is going to be large positive number and then times 3. So who cares? And that implies that f of x is increasing on the entire domain from negative infinity to positive infinity. So it's always increasing. And we know that, right, again, because this is one of the basic things to graph. It looks like that forever. So it is increasing from negative infinity to positive infinity. So that's the basic concept. Now we're going to take a look at a little bit more involved. Let me just do one more time the summary. So first derivative test detects the increase and decrease in a function. And then when the increase changes into a decrease, that's a max, right, at the critical point. And when the decrease changes into increase, that's a min, again, at the critical point. In terms of the partitions, to find those b values, which are the test values, you are going to partition the number line using the critical numbers and also vertical asymptotes. So we're going to take a look at one problem like that with vertical asymptotes, hoping that, let's see if the book has anything on it. Whatever. So let's talk about 1 over x squared, because we can. So f of x is equal to 1 over x squared. I will spell it out. Find the intervals on which the function is increasing or decreasing. Find all min/max. Now, if you know how this function looks like because you memorized it, then you immediately have the answer to all of this. You write it out and you're done. But if you don't know how graph looks like, and if you don't have the calculator, we have to figure out the whole procedure. So f of x is x to the minus 2. We immediately find the derivative, which is negative 2x to the negative 3. And we set that equal to 0. So I have negative 2 over x cubed is equal to 0. No solution. Implies no critical points. Implies no min-max. So we immediately eliminated the second part of the question, find all min and max. There are none. But then there is also find the intervals where the function is increasing and decreasing. which means we can still do the first derivative test. However, you have to remember that this function has a vertical asymptote at 0, so 0 will be still partitioning this, and we are choosing two test points, -1 and +1. So I'm going to point the arrow here and say because of the vertical asymptote. So we do have partitioning. Again, we create those two boxes to the left and to the right. Now, sometimes you're going to have 5 of these, right? Now we only have 2. We only have one point at which we are partitioning, which gives us 2 pieces. If you have 4 points, critical points and vertical asymptotes, let's say together, then you're going to have 5 regions to test. So we have this particular setup now, and I'm going to test the f prime computed at -1. F prime was -2 divided by -1 cubed, which is +2, larger than 0, implies that the function is increasing. Now observe, where is the function increasing? Function is increasing from -infinity to 0 on this part of the line, the left. So increasing on -infinity to 0, you do not include 0. There is no need to worry about increase and decrease at the single point. So we do not include 0 in this. F prime computed at 1 is -2, 1 cubed, which is -2, which is less than 0, which implies that f of x is decreasing on 0 to infinity. Now, I'm just going to point to these two and say parts of the domain. Parts of the domain. And we'll have decrease. Observe that we do not have a maximum. There's no maximum because it's a vertical asymptote, right? It's a vertical asymptote there. So you can't have a point along the vertical asymptote. Now, the problem is solved, but what I want to do is I want to add the graph for this, for those of you who don't know it. And now when you look at this graph, hopefully it's clear that you have increasing function coming out of -infinity, increasing function, and it stops at 0. And then the function becomes decreasing after 0. So for positive values of x as the input, all of the values now diminish, which means it's decreasing function. So our first derivative test, even though there are no critical points to be min and a max, still, well, actually the whole thing is designed for figuring out increase and decrease. And then as the byproduct, we figure out min and max once we have everything else calculated. That's the procedure. There's going to be 1 out of 13 steps for next class to graph the function by hand. Don't want to miss that. So I will put up one problem for you. Do the same thing. Find the derivative, set it equal to 0, find the critical points, and then work out the rest. F of x, this is problem 34 in the textbook. F of x is equal to x squared minus 2 ln x. Again, the goal is not to graph. Don't even bother graphing. We don't need the graph. All we need is the first derivative equal to 0. Find the critical points. As soon as you take the first derivative, ln x goes away, so Don't be freaked out now. Take it away. That one's square. Yeah, I'll definitely buy something. You know, roughly the matter. Okay, let's take a look at this together. This is very structured. 1, 2, 3, done. We find the first derivative, which is 2x minus 2 over x, and we set that equal to 0. To solve this, 2x is equal to 2 over x, which is 2x squared is equal to 2, x squared is equal to 1, x is equal to plus minus 1, two values. Right, if you square root both sides, you put plus minus. So here are our critical numbers. And now this is where, and I'm going to actually use the red color to emphasize some of the pre-calculus knowledge that it's needed to do analysis before you actually are successful with these problems. You need to use your eyes and know that there is ln x in a problem. Ln x has the domain 0 to infinity. And that is very significant because that means that the entire function inherits that domain. So x squared has domain from negative infinity to positive infinity. But you have to go for the entire function, right, which is combination of polynomial and the ln. For the entire function as a combination of the two, you have to go with the more restricted domain. Think of this. You are at the train station. The train is leaving slowly. Doors are still open. If you run, you can catch it. Right? That would be x squared. But then you are with your grandma and she is like, right? You're gonna miss it because there's a restriction. All right? You can move as fast as she does, otherwise you ditched her. All right? Unless she doesn't remember stuff, in the case it's fine. So you have the restriction here. This function has the domain 0 to infinity, which means that -1 as a critical number doesn't matter. Further, ln x has a vertical asymptote at 0. That is also going to be a place for us to do partitioning. So when we draw our line, we put the tick mark at 0 and then at 1. And we don't need anything before 0 because it doesn't exist because of the domain. So now if I draw a partition, I can literally start partitioning at 0 and at 1. So I choose my test points half and 2. It doesn't matter. So now I run my first derivative test, f dt. First derivative test. So f prime of a half. We simply compute that, which is 2 times 1/2 minus 2 times divided by 1/2, which is 1 minus 4, which is -3 less than 0, which implies that f of x is what? Decreasing. Very good. You put the arrow going down. Then we compute the f prime at 2, which is going to be 2 times 2 minus 2 over 2, which is 4 minus 1, which is 3, which is larger than 0, which implies that the function is what? Increasing. Now we know that at 1 we have a critical point. At 1 we have a critical point. We can compute f of 1, which is 1 squared minus 2 times ln of 1, which is 1 minus 2 times 0, which is 1. So we know that we have at 1, 1 critical point. And looking at the chart up there, what is it? What is it, this critical point? Looking at the chart. Minimum. One is the minimum. Now you can already even sketch this because you know that at 1, 1 is a minimum. You know that the x equals 0, which is y-axis, is the vertical asymptote. So the function has to go like that. This being a minimum, the lowest point, and then the function has to rise from there and go away. This is now just a sketch. We're going to do a much better job at drawing this function by hand on tomorrow. Tomorrow, 4.3, graphing all kinds of nasty functions by hand. And first derivative test is going to be one step in the procedure. Good. Second part of this lecture is going to be second derivative test. Second derivative test. And that one detects concavity of the graph. What is concavity? Well, let's first talk about concavity. Concavity looks like this. This shape, the entire shape, is concave up. Think of it as holds the water, all right? And this shape is concave down. Spills the water. Now we can actually break these shapes into halves. So if you have a piece like this, piece like that, both are concave up. And you have a piece like that, piece like this, both concave down. Further exploration here, I would like to make distinction between and connection between increase, decrease, concavity up and down. And the best thing to use here would be investments and money, so business side. We're going to take a look at 3 portfolios which invested initially the same amount of money over the same period of time. So this is the time axis because money gets accumulated or lost over time. And this is the money axis, meaning how much money you have in the account. Let's start each single one at the first tick mark. I don't know, representing $100, $100,000, it doesn't matter. So that's the initial amount of money for all 3 portfolios, the same. And then we have this one, and that one. Which one over time makes most of the money? Number 1, 2, or 3? I heard 2 and 3. Is it 2 or 3? Should we take it outside or something? 2 or 3? 2. Why 2? Sorry? They all go up forever. All of them. All 3 of these go up forever. So, despite the fact that all 3 of these are increasing, the first one is increasing constantly, the second one is increasing at the increasing rate, and the last one is increasing at the decreasing rate, right? So this one is definitely slowing down. We see that. And this one is speeding up, and this one is always flat like this going on. So number 2, second one, definitely, second one, very good. So second one is the one that would make over time most money, and that's the concave up one. So if you look at these 3, all 3 are increasing, which means that if you spend time, right, you wait, you will make money with all 3 portfolios. But now we are looking for that edge. Where do I make more money? Like, which one of these makes most money? And that will be second one. So you have, over here, you have that it's increasing and concave up. The number 3 is increasing and concave down. So let's write that. This one is increasing, no concavity. This one is increasing, concave up. And this one is also increasing, but it's concave down. And we definitely want this case over here because that one makes most of the money. So I hope you guys understand what concavity is. The procedure for second derivative test is identical to the first derivative test. It just detects different thing. So second derivative test as dt is second derivative of x equals to 0 will give us x equals some number a called the inflection point. Sometimes, in some cases, that inflection point is also detected by the derivative, first derivative. Sometimes, not always. So now we don't have critical points any longer. We have inflection point. Inflection point, I will give immediately definition, is where the concavity changes. Now, how about the test? Again, partition with all A's and vertical asymptotes. Pick test values B, and then we have if f double prime of B is less than 0, then function f of x is concave down. Okay, I'll be right with you. And if the derivative at B is larger than 0, then f of x is concave up. So hopefully you're seeing the same thing, except you're not using first derivative, you're using second derivative. So let's do this on the cheapest possible problem, y equal x cubed first. So we have the first derivative, y prime or f of x prime, whatever, is going to be 3x squared, and the second derivative is immediately 6x. Set that puppy equal to 0. You get 0. Find the y value for 0 is 0 cubed is 0. And we have our 0, 0 inflection. Once you have the inflection point, we do the partitioning here. There is 0. Choose, again, -1 and 1 because we can. It's x cubed, so it has the whole domain, so we don't have to worry about that. And just run the test. So second derivative test is f double prime computed at -1 is going to be 6 times -1 is -6, which implies, right, which is less than 0, which implies f of x is concave down from -infinity to 0. The second test point you picked is 1. 6 times 1 is 6, which is larger than 0, implies that the function is concave up on 0 to infinity. So concave down, concave up. That's all you need to write. Let's So let's take a look at an example from the textbook. And now we know how to find everything, right? You have a function. You can find critical points which give you min and max. You can find second derivative set equal to 0, get the inflection point. You can get concavity. So you have everything: min, max, increase, decrease, and concavity. That information should be enough for you to put the lines together to draw. So we're going to just add x-intercepts, y-intercepts, asymptotes, few little things here and there tomorrow to graph functions by hand. And you literally can go and say, okay, sine of ln x squared looks like this. And you just draw it by hand because you did all the derivatives and things. It's going to be awesome. Epic. No, epic. Epic. That's the word you use. Epic. It's going to be epic. So let's take a look. We'll start. Let's start slow. There's no slow with the book. They go with 2x squared ln x minus 5x squared. Sounds like good times, right? So let's first do x to the 4th. So here, problem 58 says f of x is equal to negative x to the 4th minus 2x cubed plus 12x squared. So first derivative is immediately minus 4x cubed minus 6x squared plus 24x. And the second derivative is going to be minus 12x squared minus 12x plus 24. Now they're only asking us for second derivative test, but you know what? Let's first as well, why not? So let's go with the first derivative test. That means that the first derivative needs to be set to 0. Now you can factor out negative 2x. And you are left with, so negative 2x is factored out. You are left with 2x squared plus 3x plus 12 equal to 0. So that's what you're left with. No, minus 12, because we are factoring out negative 2. So negative 2, good, and then negative 6, and positive 24. Awesome. So now we solve this. Negative 2x equals 0 from where x is 0. That's our first critical number. And the second one needs to be factored, right? So what are the factors here? 2x times x. And is it 2 and 6 or 3 and 4? 2 and 6 or 3 and 4? Well, let's just try. 3 and 4. So we have 3x and we have 8x. So let's swap them, 4 and 3. So then I have 6x and I have 4x. You know what? Let's just factor this. Depending on how fast you can compute, negative 3 plus minus square root of 9 minus plus 4, that's 40, right? 48 times 2 is 90. For AC. So 4 times this is 48, so 96 divided by 4, and 96 and 9, that's 105. There's no square root of that. So, I mean, there is square root of that. It's not the whole number. So negative 3 plus minus square root of 105 over 4. Those are the values. Now, I really don't need to know how much all this stuff is, because I'm just partitioning. So I have negative 3 minus square root of 105 over 4. Then I have 0. And then I have a positive. So negative 3 plus 105 over 4. So I can pick test values. Square root of 105 is close 121, so call it 11. It's not 11, but call it 11. So minus 14, so roughly minus 14 over 4. So like between negative 13 and negative 14. So we can pick negative 10 and negative 20. The other side is symmetric, pick 10 and pick 20. And we can compute each one of these in the first derivative to check intervals. So the first derivative computed at negative 20. Yeah, that's a lot of calculations there. All right, let's get this over with quickly. What I'm going to do is type this in a calculator as a function and quickly compute. So negative 4x cubed minus 6x squared So for negative 20, we get negative 40, less than 0. I'm just going to put decrease. Then we have, oh wait, that was negative 2. Did not get the 0. Sorry. It's 29,120, which is larger than 0, which is increasing. There we go, much better. Then we have same thing with negative 10. Again, positive value. So still increasing. Then we have positive 10 is negative 4,360, which is less than 0. So now we have a decrease. And the last one is with a 20, which is negative 33,920, which is less than 0, which is another decrease. Awesome. So we know there is a max at 0. X equals 0 will produce max once you find out. Well, 0, 0 is right. Yeah, 0, 0 is max. Good. So now second derivative test is when you take the second derivative and set it equal to 0. Second derivative was, we can factor out negative 12. So factor out negative 12. And we have x squared plus x minus 2. Equals 0. these guys, these factors out, right?
Your class loves you. Your next class loves you. They want to come in here so bad. I think these values that we picked, it's not 13 or whatever. It's like, I don't think, you know how we went like 13 and 13 on either side of
13 to 14, yeah. That's why I picked 10 and 20.
It's not. I think it's only like 3-ish.
Square root of 100 is 10, right?
Yeah.
And then minus 3. Oh, then divided by 4.
Yeah. It's 3.5.
All right, I'll have to fix that the next class because these guys are waiting outside. So we'll just fix the values next class. But you actually you can fix it for homework. What else you gonna do tonight? I mean.